All right, let's go ahead and get started here. So I posted the code from last week to the GitHub, and I included some examples about move and copy constructors for you to review on your own. I'm not going to go over them here because, like, I just explained it all in comments, and it basically is the same information we covered on Wednesday. It's just a lot cleaner and less confusing. And there's some extra examples in there as well. So that stuff is important. You don't have to understand it fully, but like as long as you get the concept of what a move constructor is, the basic differences between L values and R values, then you should be fine. But those concepts will be important later on, so that you understand like why I write things a certain way. But yeah, this week we're starting the interesting part of things. We are going to start on our graphics library. So for this game engine project, we're using OpenGL, which I've talked a bit about. It's sort of like the oldest like standard graphics API came about in the late 90s. And the reason it was standard and why that's important is because there are a lot of different hardware manufacturers. And in the late 90s, when hardware acceleration for graphics was starting to become more popular, especially 3D acceleration for graphics, it was very important that you could write code, once with minimal amounts of changes to target a bunch of different systems, because you don't want to have to learn a whole new API for every different brand of graphics card, right? And that pattern has obviously been very successful. OpenGL is the most widely used graphics API in the world today, still, I think. There are some newer ones, DirectX, which is Windows specific, Vulkan, which is maintained by the same group that maintains OpenGL and is a bit more modern. But either way, we're using OpenGL. It's a bit old, a bit outdated, but it still works fine. Before we get into any specifics about OpenGL, though, let's just talk about like basics of graphics programming in general. So we'll go through this presentation, then we'll start setting up our OpenGL stuff in code. So a pixel, you probably know most of this, but a pixel, it's like the smallest unit of computer graphics. Each has a red, green, and blue component, RGB. During the rendering process, they're often assigned a fourth value called alpha. And this is just used to blend colors. It's like opacity. But once the final color is resolved, the alpha value doesn't matter at all. Your monitor just takes in the red, green, and blue components. So a computer screen, in memory, like abstractly, is just an array of pixels, and it's stored at some location in memory. That location is OS protected, meaning that you can't just like get a pointer to that and go there. Windows won't let you. Mac OS won't let you. But you can access it. You just have to do it through operating system functions. So you don't have direct access to it, but you can write to it, obviously, so that you can change what's displayed on the screen. And that's part of what OpenGL does for us. Is it handles this part of things, so we don't have to worry about that. OpenGL creates a frame buffer, which is basically just an array of pixels, like I was saying, and it draws the values there. And then once the frame has completed the rendering process, so everything that you're drawing is accounted for and has been given a value in the frame buffer, that frame buffer is just copied to wherever the screen is located in memory. And then obviously that is then drawn on your monitor. So a bit more about the frame buffers. Is OpenGL normalizes its coordinate system. So even though the frame buffer is going to have, like in a lot of cases, dimensions of 1920 by 1080 pixels for a standard HD monitor, the coordinates that OpenGL uses are always between -1 and 1. So maybe normalized isn't quite the right word. I think technically that means between 0 and 1. But either way, the point is that no matter the actual number of pixels, it's a floating point value between -1 and 1. -1 is the bottom left, meaning that the negative x direction is to the left, and the negative y direction is down. So just like your standard sort of mathematical coordinate system that you would use in calculus or whatever to graph functions. And then of course the top right is 1, 1. And this is good because it's sort of much like OpenGL handling the frame buffer or like writing to OS protected memory for us. It's just one less thing we have to worry about. We don't have to worry about what the actual size of the screen is, or the window is, I guess, that you're drawing to. OpenGL will handle all of that. It does all the math to squish and squash things no matter how the screen is sized. Now we're going to talk about triangles. So if you really just have any sort of cursory knowledge of graphics programming, you will know that the triangle is like the most basic unit of drawing something. So there are several drawing modes. You can do points, you can do lines, and of course triangles. Each of them has several variants. There's one for triangles called triangle strips, I think, or triangle stripes, something like that. I've never used it, but it's supposed to be just a slightly more memory efficient version. But we're just going to be using the basic triangles for our 2D stuff. And this is this is for a reason. This is the most widely used. There's just tons of documentation on, documentation and also examples on YouTube and Stack Overflow and stuff of how to do stuff in this drawing mode. Okay, so I've talked a bit about like what GPUs are and just that they accelerate graphics stuff. But if you're totally new to this stuff, you've maybe heard of a GPU, you've probably definitely heard of a CPU, but let's talk about some of the differences between them. So OpenGL is designed to make use of the GPU, specifically the parallelization power. So let's get a bit more into that. So there are two main distinctions. One is the scope of tasks. So CPUs are like the main processor for a whole computer. So they have to be able to do a whole bunch of stuff. And when you have to be able to do a bunch of stuff, you become less efficient at doing each of those things. GPUs are a lot more specialized, and so they can do these operations more efficiently than a CPU. But the main difference is the number of cores. Modern CPUs typically have 8 to 16 cores, but the highest end graphics cards, like the NVIDIA RTX 3090, I think, has just over 10,000 cores. And this isn't a case of like more cores means a better processor. It's not that simple. Like for most purposes, having more cores doesn't really get you much. But for graphics specifically, the more cores you have, like you're going to perform much faster. And I'll sort of explain why as we get into the pipeline. So the manner in which these cores are used is beyond the scope of an introduction. There are several different types, but we don't really need to know about that. But the main point is that the more cores you have, the more things you can do at once. Each core will be running essentially a program on that core. And when you can run 10,000 programs at the same time, you move a lot faster than if you can run 8 or 16 programs at the same time. And this is called parallelization. It's also, in the way it's used in GPUs, it's called SIMD, same instruction, multiple data, which you may have heard of as well in some of your classes. And it's extremely useful for graphics, as I was saying, because we have thousands or even millions of vertices, different triangles that need to be processed and can be processed independently of each other, meaning, they can happen on you can have a different core for each triangle or each vertex. They don't need to talk to each other. And we also have millions of pixels to color every frame. And for a playable game, that's going to be at least millions of pixels being drawn to 60 times a second. So having all these cores is really important. So let's get into the pipeline a bit and see how these cores are used. So this is the basic structure of an OpenGL program. On the software side of things, which is like the code that we will write, the C++ code we will write, there are 3 big steps. You create vertex data, so this specifies like your triangles. You describe that vertex data in some way. You say like this is what my vertex data means, this is where it's located, this is like how big it is and all of that. And then you create index data, which is just indices into your vertex data. And we'll talk about that in a bit more. Once you have these three, you upload that data to the GPU, and then the GPU uses all that data to draw stuff. There are three sort of main processes that we are going to look at on the GPU. First is transforming the vertices, so taking your data and maybe you have some camera and so you want to offset it by a certain amount. That happens in the Vertex Shader, which is code that we will write. It's not C++, it's a special language called GLSL. It's just used to write shaders, but basically it compiles down into something that runs on the GPU. Then after that, there's this rasterization process, which we don't have control over. The GPU handles all of this for us, and we'll get into what rasterization is in a minute. And then once you've rasterized everything, you color the pixels. And this is another thing that we're going to be doing in GLSL. It's called a Fragment Shader. And basically the Fragment Shader runs one time for every pixel, and the output of the Fragment Shader is the color of that pixel. Now I've separated these into two different boxes here. The CPU stuff happens one time with a little asterisk. Obviously it's not going to be exactly one time. There are some cases where you might sort of dynamically create vertex data, like maybe you have a map editor or something, and like you don't know all the stuff you're going to need to draw when you start the game, so it can't be hard-coded or anything like that. And also if you have sort of dynamic objects moving around the screen, you're going to be updating their vertex data, obviously, to say, okay, it was in this position, I'm going to move it to this new position. But compared to the number of times that this GPU stuff happens, it's basically once. It's essentially like a constant amount of work. The GPU stuff, though, happens every frame, which again should be at least 60 times per second. So let's go into each of these steps a bit more. We'll do the CPU first, and then we'll do the GPU. So we have to create vertex data. What is a vertex? Well, you might consider a 2D vertex. I'm going to do everything in 2D because there's no need to complicate it with 3D stuff. We're only doing 2D graphics in this course. So you might consider it to be just like this, just a single point with an X and Y coordinate. That's absolutely true. That is a vertex. That's a 2D vertex. You need at least that much data to draw anything in 2D space. But in OpenGL, vertices have a slightly different meaning. They contain a whole bunch of data. So this is the format we'll be using eventually. You have X, Y, ST, and then I. So you have the base X, Y space values, which again are required. Then you have ST, which is essentially another XY pair, but it's a texture coordinate, which I'm not going to get into now. And then I is our texture index, which I'm also not going to get into now. But essentially just know that a vertex is not necessarily only space data. It contains other data. So once we have a vertex data, we need to describe it. So let's just take this example array of floats here. You can see we have 4 vertices, each with 5 floats. This is just using this XYSTI layout over here. So we have 1 at 0, 0, 1 at 0.5, 0, 0.55, 0.5. Those are our X and Y coordinates. Then we have texture coordinates here and texture indices. So we know, based on our sort of abstract model of, well, each vertex has X, Y, ST, and I, and it's more or less obvious from the way we've laid out our code here. But OpenGL has no idea what this is. It doesn't know how to read this. You just give it a bunch of floats, it sees a bunch of floats, and it doesn't have any sort of information about them. So you need to specify that information. For example, how many groups of numbers are there in each vertex? Well, we have 3 groups. We have XY, our position, ST, our texture coordinate, and I, our texture index. It also needs to know the byte offset of each group from the start of each vertex. So basically, where is this data located? And in our case, this would be like for XY, obviously that's at the start of the vertex, so it would be 0 bytes. For ST, it's 2 floats in to the vertex, so that would be 2 times 4, because floats are 4 bytes each. And then it needs to know the total size in bytes of each vertex. So I've just sort of separated these out here. You can see by column we have our x values, our y, st, and I, and then we have 3 different groups. Group number 1 is our space coordinate pair, the x and y. Group number 2 is our texture coordinate, and group 3 is our texture index. The size of each is just the number of bytes in a float times the number of floats in that group. So for x, y, we have 2 floats, so 8 bytes. For st, we also have 2 floats, so 8 bytes. And for I, we just have 1 float, so that's going to be 4 bytes. And then the offset is basically the sum of all of the sizes of the groups coming before it. So for x, y, because there are no groups before it, that's 0. For st, there's 1 group before it, so that's 8. And for group 3, there are 2 groups before it, so 8 plus 8 is 16. And then if we had some 4th group after I, the offset would be 8 plus 8 plus 4. So once you have your vertex data and you've told OpenGL what that data is, we need to create index data. The reason we do this is because many of the triangles, in our case especially, because we're just doing 2D rectangular textures basically, will share vertices with other triangles. And we want to avoid copying vertex data as much as possible, because there's no reason to do that. It's just inefficient. So we use something called an index buffer. Using an index buffer, you only need to create 1 copy of each vertex in your vertex data, and then you can reference that in your index data to say, use this vertex, and this other vertex to draw me a triangle. So for example, if we had this quad here, just a square, you can see there are 2 triangles. We have the one between 0, 0, 1, 0, and 1, 1. This bottom right one here, and then we have the top left one, which is between 0, 0, 1, 1, and 0, 1. And if you notice, we copied 2 of these vertices. 0, 0 appears in both triangles, as does 1, 1. So that's a lot of unnecessary data. So instead, we can assign an index, a unique index, to each vertex. I just went counterclockwise here, which is slightly important. I'm not sure if I'll talk about why, but there is a reason for this. So we have 0, 1, 2, 3. Now, we only need 1 copy of each of these XY pairs, and then we can instead draw our triangles using these indices. So the bottom right one, instead of 0, 0, 1, 0, 1, 1, would be 0, 1, 2. And then the top left, similarly, would be 0, 2, 3. Okay, so once we've got all of our vertex data, we've described it, we've got our index data, and we've sent all of that to the GPU, it's time to transform our vertex data. And once again, now that we're doing GPU stuff, these operations happen once per frame. So once our data is on the GPU, we process it with our end goal being to get some image to put on the screen. And the first step is to transform the data. For 2D stuff, I can't really think of another thing other than like maybe scaling stuff if you have some sort of zoom functionality in your game, and just translation operations to simulate a camera that could be following your player or something like that. But for 3D stuff, it's much more involved. It's very optimized. I really don't understand it at all. I have done a minimal amount of 3D graphics programming, but it uses 4D matrices. It performs translation, rotation, scaling, perspective projection, which is just to simulate like the way your brain processes light. And then it also has to worry about clipping, because in 3D space, like some points could be in front of the camera and some could be behind, and that causes sort of mathematical oddities. So that's a lot more involved, and it's a big reason we're not doing 3D stuff. But essentially the transformation step here, it takes data from world space, which is the sort of coordinate space that all of our vertex data is in, and transforms it into screen space, which is as it would be seen by the player, but also into pixels on your monitor, right? It has to take this sort of abstract space that we've created and map it to that -1 to 1 range that OpenGL uses for the frame buffer. So these happen in a program on the GPU that we will write called a Vertex Shader. It's run once per vertex, and the output of the program is the screen space position of the vertex. Okay, now let's talk about rasterization, which is that automatic process that happens on the GPU that we don't have any control over. So now that our vertices have been transformed and they're where they should be, they're still in this sort of weird, like fake -1 to 1 range, right? And we need to convert them to real integer pixel values on our screen. This step loses some accuracy. It's just a quantization process. It takes this, not technically, but theoretically, continuous range of the -1 to 1 float values and turns them into or maps them onto, I should say, this discrete range of integer pixel values. But in terms of like being able to resolve detail, modern displays have enough pixels that this accuracy loss doesn't really matter. It does look a bit janky though, and so for 3D stuff, there will often be some sort of automatic post-processing effect called anti-aliasing, which like takes jagged edges and smooths them out by adding some extra pixels here and there. But we're not going to deal with that. So let's say we have this triangle, this sort of smooth line triangle in our OpenGL -1 to 1 coordinate system. And interesting, actually, this was done in Paint. You can see here these jagged lines. Anti-aliasing would smooth that out. That's sort of an interesting example, just included by accident there. So we take this data, and we have to map it into integer pixel coordinates. I went for pretty low resolution just because it was tedious to copy all these triangles. But you get the idea. Like, it takes this, and it tries to fit as many pixels as possible into it, and generally does a good job. Like, it maintains the sort of basic shape of it. But just knowing where these pixels are isn't enough. You have to add color to them. And this is technically part of the rasterization process, but I've separated it because we have control over this. Remember, rasterization is performed by the GPU, but the color of pixels is entirely up to us because we are writing a fragment shader. And this shader, similarly to how the Vertex Shader runs for every vertex, the Fragment Shader runs for every pixel. And the output of the Fragment Shader is the color of the pixel. So eventually we're going to be using the texture coordinates, those ST pairs in our Vertex data, to sort of sample from a texture at a given point. And we'll go into that more when we actually start doing that. Yeah, so that's the end of this sort of crash course in graphics programming. Does everyone sort of know where we are and like what our goals are and what the steps are? All right, thanks. All right, so now we get into the interesting part of this project. All the math stuff up to now has been pretty boring, but now that you're all warmed up with C++, let's get into graphics. So I'm going to create a new folder here. I'll call it GFX for short. And this will be sort of another top level folder at the same level as my math and source folders. I'll add 2 new files, just like our math library. This is just sort of a convention I use, having this all.h file, which like includes everything in the GFX folder, and then this core file, which just has like not really anything in particular, but still data that is necessary. And I'll go ahead and close all of this math stuff. Trying to lay this out in a way so I don't have to scroll as much. Okay, and then I will zoom in a bit. All right. So in our all.h file for now, we're just going to include core.h, of course, And then we will also include this all.h file in our pch.h. GFX/all.h. PCH, again, is in the source folder, and it's sort of like the main include file for our engine. So once I've got that, we can start working on the core.h file. So here's where we're going to include all of our graphic stuff. I sort of have it right now in this pch.h file, just because as part of the setup for this project, I had you do that simple window example. But that shouldn't really be there. This should be in our graphics library, the thing that handles all the graphics. So I'm gonna take that out of pch.h and put it in core.h. This won't matter. It doesn't really matter where it is. I just like it as for organization purposes. So once we've got that included, I'm going to do a simple type def here. We did more of these in the math library, but we're just going to use the uint here, just so we don't have to type out that 32_t every time. And the reason I'm not, I'll just go ahead and open it. You can see we did these already in our math library core file, but the reason I'm not including that is because we want our math library and our graphics library to be independent. They should be, like, if we were actually writing a proper library here, you would want that library to have 0 unnecessary dependencies. Obviously, for our graphics library, you need OpenGL stuff, but you should, beyond that, just be able to sort of drag and drop all of this code into your program, and it should just work. It shouldn't require any other weird libraries or anything like that. So that's why I'm just doing this sort of ugly redefinition of uint there. So the first thing we're going to do is sort of wrap all of that stuff that we did in the setup, that you did just to get a window showing. We're going to wrap all of that up in our core file here, and then call it from our main function. So we're going to need a couple of structs here. I'll start with OpenGL instance. And note now that I'm doing namespace GFX instead of namespace math, just to keep things separate. And this will have a glFW window pointer. I'll just call it window. And then a single Boolean saying whether or not it's running. So we'll use the glFW window should close function on our window. And as far as I know, this just returns true, like if you've hit the red X in the top right of it. Okay. And now we're going to write an initialization function that will take in some parameters, set up OpenGL stuff, all the variables we need, and then return one of these OpenGL instances. Call it init. We're going to take a width for our window, a height for our window, a string that's the name of the window, and then we'll add another thing on the end there in a minute. So first we're just going to do glFW init. In our case, we don't really need to do this error checking stuff because we already know it's working because we've tested it before. But again, if this were like a real graphics library, you would want this stuff just so that the user doesn't have just sort of random crashes with no error output. The program should tell them what's going wrong if anything does go wrong. So then we'll do, if this init function returns false, that means it's failed. So we'll say failed to initialize GFW, stop it all, and then we'll just return sort of a nothing object. Because remember, we do have to return something. We have to return an OpenGL instance, but we don't even have a window pointer at this point, so we'll just give it null pointer. Oh, it seems I don't have printf. Just include standard IO. There we go. Okay. Now we're going to set up some essentially variables for GLFW. You set these using GLFW window hint, and you have to give them this sort of macro value, GLFW resizable, and I'll say false for now, but we'll come back to that in a minute. So this just makes it so that you can't drag in the corner of your screen and make the window bigger or smaller. Now we're going to do some stuff that is necessary in our case because we are dealing with people on Macs and people on Windows machines. We need these GLFW context version major and minor. I'm just setting both to 3 because I believe that's the minimum version required for all the stuff we're doing. There are newer versions. There's 4.2, maybe 4.5 is the newest. I'm not sure. But because we're just doing simple 2D stuff, we don't need all of that. And then another thing for the Mac users, we need GLFW OpenGL core profile. I'm not sure exactly what this does. There's probably documentation on it. So I won't go into it. I have some ideas about what it is, but basically it's just another thing we need to get this to work for everyone. As is this, the GLFW OpenGL forward compat. And what this does is it says, okay, so I have this version major and version minor stuff. If I can find any version of OpenGL that is at least that, I'll use it. If we were to set this to GL false, it would only take version 3.3 of OpenGL, which we don't want. Because again, we have a bunch of different people on a bunch of different systems, and we want it to work for all of them. Okay, now that's out of the way, we can actually create our window with the GLFW create window function. We'll give it the width, height, and title that our function took in, and then this monitor and share stuff. I think I know what monitor is. I'm not even sure what share is, but we'll just give null pointer for both of those. Those don't matter. And then we will sort of, I guess, bind this window to OpenGL with the make context current function. Now at this point we'll have another error check because window creation can fail. This GLFW create window function can fail, and if it does, it returns null pointer. So this just says basically if window is a null pointer. We'll say window creation failed. Then we will shut down GLFW and return that same sort of nothing object. Oh man, I can't type today. There we go. Okay. So this has set up our window. Now we need to, again, I'm not going to go into this, but we need to sort of bind all of our OpenGL functions. We need to make it so that we can use them. Because at this point, our program knows those functions exist, it knows what the names are, but they don't actually point to anything, which is a problem. So we're going to set this glue experimental value to GL true. I can't remember what that's for. It's very common that this has to be set to true though, because again, we're not doing anything like crazy. But we'll just set that to true, and then we'll do glue init. And confusingly, glue init returns true if it fails. It's sort of the opposite of GLFW init. So if this returns true, print out another error message. Failed to initialize glue. And at this point, because we have a window, we should properly dispose of it with GLFW destroy window, like that. And then GLFW terminate, returning our sort of error object again. So now that glue has been initialized and we can actually use our OpenGL functions, we can set some more parameters. So we'll set GL clear color, which is just sort of the background color of the screen for any pixels that aren't filled in by the rasterization process. I'll just set this to blue for now. And you can see the alpha value here. It doesn't actually do anything, so I'll just put 1. Then we have GL enable, GL blend. So this is for using that sort of fourth component of pixel colors, the alpha value, to combine different colors if they are somewhat transparent. And then we'll set our GL blend func to GL source alpha and GL1 minus source alpha. And you can see probably from the sort of autocomplete suggestions there are like a bunch of different things for this. I don't know what they all do, but I just know that this one is like intuitive regular color blending. Okay, and now even though we've set, just for now, we've sort of hard-coded this resizable value to false, we'll change that in a minute, and when we do resize our window, we want OpenGL to respond correctly. So remember how I said that the frame buffer is, it's just an array of pixels, but OpenGL normalizes all the coordinates between -1 and 1. And when we change the size of our window, the size of our frame buffer, those calculations can get messed up. So we need to use this other function called glViewport, which basically, as far as I understand it, resets that normalization range. It like recalculates which value should be 1 and which value should be -1. And we want to do this within a callback. So we're going to give a function that runs whenever our window is resized. So this is glfw set window size callback. We want to set this for the window that we've created. And then you can see here the second parameter is this glfw window size fun. Now this I'm not going to go into. We're going to do something a little weird, just because I don't want to define like a whole correct function for this. We're going to use something called a lambda, which if you're familiar with JavaScript, you've certainly seen them. Java as well has them in the newer versions, but it's just sort of like an anonymous function that you can write in line. And these functions, they take a glfw window pointer, they take in the new width of the window after it's been resized, and similarly the new height. And then inside of this, so when our window has been resized, we want to call glViewport, with the xy being a 0, 0. We don't want to offset that, but we do have a new width and a new height. So we'll give that to glViewport. And there we go. Then of course, the last step, we've set all the stuff we need to set, so we will return a proper object, which just contains the window pointer that we've created. Okay, now we have this init function. We should also have like a dinit function, or just an end function. So this will be static void. I'll just call it end. And we'll take in an OpenGL instance called instance. And then we just need to do all of this like terminate stuff that we've done up here. So first we'll destroy our window. glfw destroy window on instance.window, and then glfw terminate. So init will be called at the beginning of our program, and end will be called at the end of our program. Okay, so now that we have this, let's go into main and specify some stuff. So I'm going to get rid of all this. If you haven't read through that yet, just sort of comment it out for now, because it is important. But in the sake of making my code readable to you, I'll just delete it. So we need, yeah, sorry. So we're just destroying our window and then terminating glfw. And there's no glue terminate. It's not that I forgot that, it just doesn't exist. You got it? All right. So in our main function, we're going to create an OpenGL instance. I'll call it GL by calling the graphics init function. I'll make mine an 800 by 600 window. The title is title. And then just before we return, I'll call GFX end on that. And let's run and see what we get. There you go. So that was sort of a a very brief example, but you can see something did pop up. I'll run it again just in case you missed it. Boop, and we have no error output. If we want like a sort of better test of this, we could do while gl.isRunning, that method we specified, and we'll do all the proper stuff in here. So first, we need to clear the screen at the start of each frame. We do that with geoclear on color buffer bit. Now, geoclear, it performs an operation on the current frame buffer. And if you could tell by this, there are several components that a frame buffer can have. There are the one that I think we're going to be using later on is the depth component. But for now, we just have color, so we're just going to set the color to our clear color, which in this case we set over here is blue. Then we'll do glFW swap buffers, which will just, so like we clear the screen, then in here we draw everything, and then when everything is done drawing, we will move our current frame buffer to the screen. And then at the end, we'll do glFW poll events, which we're not going to use just yet, but this is for stuff like input, which is another nice thing about glFW is that it handles the window creation and management stuff for us, but also the like operating system events that run through that window. So like if you have this window selected and you press a key or move your mouse, it will handle all of that when you call glFW poll events. Okay, so now if we run this, we'll just see this blue screen up here called title, and you can't resize it. So this is exactly what you should have had for that, like the initial setup step. Okay. So we're going to come back to our init function just for a bit here and specify some extra options we can set. So like we've hard-coded this resizable value, we've hard-coded the color. There's not really a need to do that. And I'm going to do this the same way as I did the, what was it, the range contains param stuff from Wednesday, where we have like a structure that contains these sort of optional values. So we'll define that in a minute. I'll call it window options, and we'll default initialize it. And then for our resizable value, oh, I didn't give it a name. I'll call it options. And again, I'm giving it this default value with the equals and then empty braces. So we'll set our resizable value to options.resizable. Did you, in your pch.h, did you include graphics/all? Okay. In your graphics/all function, did you include core? And it just says it can't find this namespace? Oh, so it is finding the namespace, it's just saying that doesn't exist. Could you share your screen on Discord? I think you've spelled GL instance differently. You did uppercase G, lowercase l in your core.h. Yeah, that should fix it. Nope, no problem. I'm actually going to take 1 second and go get some water. All this talking has dried out my throat. I'll be right back. All right, sorry about that. Okay, yeah, so we have this window option structure, and all we want in there is a Boolean for resizable, and then color values of R, G, and B. So let's go ahead and write this. Struct window options. We have a bool resizable. We'll give that a default value of false. And then we could do like float R, G, B, like that. But then from a user standpoint, they have to specify all of these, and it's just, I don't know, it's a bit of a pain. So I'm going to create another structure here called color, and this will just store those for us. Just keep things a bit more organized. And I will initialize that to 000 or black. And then here we'll have color, I'll call it clear, and just default initialize it. So now we take in a window options, and we're going to use this resizable method to set as the GLFW window hint here. And then we will use our RG and B values in this clear color. So I'll do options.clear.r, clear.g, and .b. There we go. So now if I run this, it should give us the exact same thing, because our default values, oh, well, not quite the exact same thing, because I made the default color a clear color of black, which I think is reasonable. I still prefer to have it like that sort of garish blue color, just because it makes it a bit easier to catch like graphical bugs. So in our call to init here, I'm going to specify that B as being 1.f. And this is the cool thing about having all of those default values is even though I'm giving it a structure here, I don't have to set resizable. I don't care if that's true or false. And I don't have to set the R and G components of the color. I just have to set the one I'm interested in. So now if I run this, it should be exactly what we had. And that's perfect. And I guess I could go ahead and set resizable just so you can see. But we won't really get to test the effects of that until we're drawing stuff and we see that the GLViewport stuff works correctly. But you can see now that I can grab and drag my window. But I'm going to leave resizable off as false. Okay. So now that we've got this going, we're sort of just going to hard code a bunch of stuff. And I think we'll just about get through this part this time. And then we will start actually like abstracting everything out into classes and doing it properly next time. But I think it's important that you see what the goal is and how we get there before I just jump into like organizing things in some weird way that wouldn't make sense if you haven't seen it before. So we're going to go through those 3 steps. I'll write them up here. Step 1 is create vertex data. And you don't have to write these comments. Step 2 is describe vertex data. Step 3 is create index data. And then steps 4 through 6 is basically draw with the GPU. So let's start with step 1. And I'll actually write it under that comment. So we need something called a vertex array. And this is useful. Vertex arrays are useful because they sort of wrap this other structure called a vertex buffer. And a vertex buffer is where our vertex data is actually stored. But the advantage of using a vertex array is that it sort of once again, it wraps that actual vertex data, but then it also wraps the metadata about that vertex buffer. So we can use this vertex array for both steps 1 and 2, just to keep things a bit more organized. Now here we're going to see this very common pattern in OpenGL, so get used to this, where you have some variable and then you call this function and send it a pointer to that variable. And what's happening here is instead of returning a value like this, you could say uint va equals the return value of that, which would be more common nowadays. It takes in a pointer and essentially returns the value through that. So this will create one vertex array and store the pointer to that array in this uint va we have here. And unfortunately, OpenGL is not very consistent about this. There are some, GL whatever functions that do return a value, but I think a majority of them are sort of this syntax of passing a pointer. And also note that the pointer returned, it won't tell me because it's sort of weird, but it returns a GLUint type, or that's what it expects as its second argument, and that's exactly the same as the uint we've defined as a 32-bit unsigned integer, so I'll just use that. Okay, and now comes another thing that's very common in OpenGL, which is binding. So we have created this vertex array, but you've probably noticed it's not like an object. It's not a structure. All we have is a pointer to it, essentially. And so in order to operate on this, we can't just like set properties of it because it's not a structure. We have to tell OpenGL, hey, I want to select this vertex array, and then all the stuff I write afterwards until I select another vertex array will operate on that vertex array. So we do this with GL bind vertex array, and we just pass, oh, there you saw it there. So this GLUint array, that's what I was talking about. GLUint is exactly the same as our definition of uint. So we pass it our pointer there, and now we can create stuff. So as I mentioned, a vertex array sort of wraps a vertex, what was I saying? A vertex array wraps a vertex buffer and descriptions of that vertex buffer. So we will create a vertex buffer now, and it will sort of be included in our vertex array, I guess. So I'll create another pointer for that called VBO, and then we'll do another glgen function with that same syntax. This is glgen buffers. Notice that it's not gen vertex buffers, it's just buffers. There are many different kinds of buffers, and we'll see a bunch of them. So now we've got this place that we can actually put vertex data. So let's go ahead and create some vertex data. I'll just call it vertices. It'll be an array of floats. And for now, just for testing stuff, we'll do just x and y coordinates. And remember that everything is normalized between -1 and 1. So I'm going to give it a bunch of 0.5s. Okay. And this goes back a little bit to what I mentioned in the presentation, which is the sort of counterclockwise ordering of things from the bottom left. So this is the bottom left vertex, and then counterclockwise next we have the bottom right, then it jumps up to the top right, and then to the top left. And the ordering of these things is important. If you reverse it and do it in clockwise order, you won't see anything. And that's not because it's like an invalid data format or anything, it's just that OpenGL has interpreted that to mean that you have basically flipped your triangle so that it is facing away from the camera. And as an optimization thing, things that are facing away are not drawn at all. So that's why you won't see anything. And I might have time for an example on that, probably not. But it's easy enough to mess around with on your own if you want. Just know that counterclockwise from the bottom left is the convention we'll be using the whole time. So now that we've got our vertex data, we're going to do, just like we did this bind vertex array, we're going to bind our new vertex buffer with GL bind buffer. And again, this is just bind buffer. It's not bind vertex buffer. And because of that, we actually have to tell it which type of buffer we're trying to bind. So we're going to bind to the GL array buffer, which is the sort of macro for a vertex array. And we'll send it VBO, which is our pointer. Now that it is bound, we can send data into that buffer with GL buffer data. Again, we have to specify, it's called here the target, which is GL array buffer, the size of our data, which we will use our handy math rsize function, which you remember it takes in some compile time allocated array and returns the number of bytes in that array, which is what this expects. Very important. If I delete this real quick, you don't have to do this, but yeah, you can see here it's called size. From what I remember, OpenGL does a fairly good job of distinguishing between size and count, where count is the number of elements in an array, and size is the size in bytes of the array. And I'll be using those same conventions just to keep things as simple as possible. So we need the number of bytes in our vertex data. Then we send it the actual vertex data. And then we have this GL enum usage here. This we're going to talk about later when we get into dynamic stuff. But for now, we'll just do GL static draw. And this doesn't matter. This won't like change whether or not you see anything on the screen. I don't think. I mean, I'm sure there's some weird values you can pass it. But basically, this just says, okay, you can optimize this as I'm giving you this data once or a very small number of times, so you don't have to write to it very often. It's just going to be drawn a lot. So we use static draw for that. Okay, so now that we have our vertex data, that's step one done. Next, it's time to describe our vertex data. And we do this, as I've been saying, through the vertex array. So this has some confusing syntax. There are methods with very similar names, and they do different things. They probably accept different arguments, so make sure you get the right one. First, we're going to do GL enable vertex attrib array. Actually, no, we're not going to do this yet. We'll come back to that. We'll just create our index data first. So what this does, describing the vertex data, as I said in the presentation, we're giving OpenGL this list of floats, and it doesn't know what they are. So we have to say, okay, there are 2 elements in each vertex, there's an X element and a Y element, blah, 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 all that stuff. But the reason we do that is so that we can then use this vertex data in our shaders. We will write some shaders today, but I'm going to skip that part for now just to keep stuff as simple as possible. So step 2, we'll come back to in a minute. What we do need, though, is our index data. So we'll create another buffer here. I'll call it IBO. I wonder why sometimes Visual Studio does this where it doesn't like give syntax highlighting for stuff. I'm just going to close my file real quick and see if that changes it. Oh, there we go. Yeah, sometimes it doesn't. Sometimes you have to like restart Visual Studio, but if you ever get that where just like certain stuff is just plain white, just try closing and reopening your file. It might fix it. Okay, so we have an index buffer object here, and we're going to use that same glgen buffers function that we used for our vertex buffer. We just want one, and we want the pointer put into IBO. Okay, so now we are going to, we're basically copying the structure of what we did up here. So this is vertex buffer, this is index buffer. So we create a pointer, we create data, we bind the buffer, and we send data to the buffer. So we've created our pointer, now we need to create the data. I'll just call it indices. And again, going counterclockwise from the bottom left, we want our first triangle to be indices 0, 1, and 2, so that's these three. So bottom left, bottom right, and top right. That makes a triangle. And then our second to be 0, 2, and 3. So bottom left, top right, and top left, which also makes a triangle. Next, we do GL bind buffer. Now, can anyone guess what I'm going to put in this target? Notice that I'm doing like the exact same stuff as up here. I am, sorry. What am I going to put in the first parameter to this function though, the GL bind buffer? It says GL enum target. Up here that was GL array buffer. Is it what? No, it's a different buffer target. Eduardo, did you? Yes, exactly. So as I was saying, we have just these generic like buffer functions. And even though our IBO and our VBO were both created with just GL gen buffers, and we're going to bind them both with GL bind buffer, they are different types. Sort of abstractly, like we know they are different types, and so we will send it to a different place. So instead of this GL array buffer, which is for a vertex buffer, we have GL element array buffer, and we're going to send that IBO. So now that we've bound it, just as before, we can send data to it with GL buffer data. Sending data to the element array buffer, and it's basically the exact same thing as above. We need the size of our data. So math.rsize of indices. We're going to send it indices. And then I'll just put GL static draw in here as well, because we aren't going to be changing this data. Okay, so I'm going to skip the shader stuff for now. And now scrolling down a bit into our sort of run loop here. Remember that each time this loop runs, it's a new frame. So at the start of the frame, we clear, we draw stuff for that frame, we move the frame to the screen essentially, and then we loop that forever until you close the window. So we're going to draw everything. We need to bind our vertex array. So I should say, I kind of did say this before, but when you do this GL bind stuff, that whatever you've bound there stays there until you tell it to bind something else. So really, like, we don't need to rebind our vertex array because we bound it up here. We didn't change it at all in here, so we should be able to just use it down here. But for the sake of like making this a better example, when we have, when we're drawing multiple groups of things that have different vertex arrays, each frame we're going to have to bind those each independently. So I'll go ahead and do that here with GL bind vertex array, even though it's just one. And then same thing for our index buffer. And remember that our vertex buffer, our actual vertex data, is sort of included in this vertex array. So we don't have to do a separate call for bind buffer on GL array buffer. That's part of this bind vertex array. Now we are going to use GL draw elements, which is the function used to draw stuff using an index buffer. This GL enum mode, as I said, is going to be the classic GL triangles. Now it needs the count, which is a lovely distinction, sort of inherent documentation. This is count, so the number of indices, not the size, the number of indices. We have 6 indices in our array here. And actually I could use math.rlen of indices if I wanted to get 6. The type of our index data, we're using uints, so that's going to be GL unsigned int. And then the indices themselves. So because we've bound a buffer here, IBO, we already have this data stored somewhere, right? So GLDrawElements is going to use that. This const void pointer indices here is for, I guess if you're using index data that's not in a buffer or something, but either way, we're not going to be using it. So we just send null pointer and there should be no problems. So once we've done that, I'll run the program and let's see what we get. Nothing. Okay. Is everyone here? Because we're about to go back and do all the shader stuff, so I don't want to. All right. As long as you've got this stuff set up, we should be good. Oh, okay, cool. All right, then yeah, in that case, let's go ahead and do the shader stuff. So we need to describe our vertex data first. Actually, yeah, okay, I'll do this in 2 steps as I was thinking, just because it'll make it easier to explain. So the reason we're not seeing anything here is because we haven't described our vertex data. We haven't said what's what. OpenGL has this data, it just has no idea what to do with it. So we're going to go back to step 2 here. Now that we've got everything set up and running, let's tell it what's going on. So we use this GL enable vertex attrib array. We are going to use, it takes this GL uint index, and I'll explain what that is once we start writing shaders, but for now we'll just do 0. And then we have GL vertex attrib pointer, and this takes the index, we're using 0, the size, which is that's an inconsistency in OpenGL, that should be the count, the number of elements in each vertex, in this, yeah, for now in each vertex. You see we have X and Y, so there are 2 elements in each vertex. The type is going to be GL float, because this is a float array. We have GL normalized, which is false. I'm not sure exactly what that is. That might be if they're between 0 and 1. OpenGL will do some conversion, but they're not. They're already in the -1 to 1 range that it expects. Now we have the GL stride, which is the number of bytes in each vertex. So that's going to be 2 times the size of a float. And then we have a const void pointer. So this is weird. I don't know why it takes this like this. As a pointer at all, let alone a const void pointer. But what this is the number of bytes between the start of each vertex and this group of data in the vertex. But because we only have one group of data in our vertex at this point, that's just going to be 0. So we do have to cast it to a const void pointer, which is a bit annoying, but it's just going to be 0. And if this were like offset by, 16 bytes, we would do a const void of 16. Very strange syntax, completely weird decision, but that's how they did it. But there's 0 bytes from the start of the array to this group. Okay, so now that we've described it, we should at least see something, because OpenGL has the data, it knows what it is, it has the indices, so it should be drawing stuff. And there we go. It's just black. Remember, we haven't drawn a shader yet, so we haven't told OpenGL, anything about how to color in the pixels. It's just using some, I guess, like default shader that exists, which is fine. So it's black. It might even be different on your system. I've seen it be white before, but either way, we've now described our vertex data. We've created our index data. So we're done with this step 1, 2, 3, this 3-step process of setting stuff up on the CPU. We've created the data, sent it to the GPU. Now we need to tell the GPU what to do with that. So step 4 is, if you remember, the Vertex Shader. Step 5 is Rasterization. And step 6 is the Fragment Shader. So rasterization happens automatically. So I'm going to take that out. We don't do anything with that. I don't think you can do anything with that. But what we can do is set our own shader code. So we need two pointers. And this is an excellent example of another inconsistency. Instead of, like we've done with this GLGenBuffers method where we're passing a pointer, these functions return the value. So we have GL, I'll create one pointer for vertex and then one for fragment. So we have GL create shader, GL vertex shader. That's the type. And then down here, I'll do uint fragment equals GL create shader, GL fragment shader. Okay, so now that we've created our shaders, we can specify the source code for those shaders. So I'm actually going to, I'm not going to separate these out like that because it'll just make it cleaner to write. Okay, so we've created two shaders, but now we need to, assign code to those shaders essentially, because once again, a shader is just code that runs on the GPU. So we've created space for that code, but we need to put code in there now. So now we're going to do something kind of annoying. We're just going to hard code the source into our program as strings. Shortly, we will be doing this through files, where we have a separate file. We read the source code in from that file and do everything there, which is a lot cleaner. But in the interest of time, again, just like getting this stuff set up so you can see what the end result is, we'll do it this really ugly way for now. So this line is very important. And an annoying byproduct of doing this as a string is I have to put the new lines in myself. But let's break this down. So this first is this hashtag version 330 core. So this is sort of a compiler directive in GLSL, the shading language, much like hashtag include is in C and C++. This 330 refers to, over here, our construct version major and minor, 3.3. And core means the OpenGL core profile, because that's what we've told it to use. So that's going to be the same for all of our shaders. Then this line is really important. So we have this layout, which I'm not going to explain now. It's used for various different things, and we'll see a different use of it later on. But then in parentheses, location equals 0. So this 0 refers to this 0, the GL enable vertex attrib array. And this is an important link to make. This is something I basically didn't figure out until like years after I'd started programming in OpenGL, but it makes it a lot clearer. So when you enable a vertex attrib array, and then you sort of set the properties of that index, that attrib array, that is directly linked to the data that the shaders receive. So we've enabled index 0 here, and in our shader we're reading from index 0. We've marked it as in because this is data that our shader is taking in. There's also out, which we'll use later on. And the type here is vec2, which is a built-in type to GLSL, which is just a 2D vector with x and y components. And I've called it I_position. So for all of my input variables, I do the I_. For the output variables, I do V_, which I'll talk about in a minute. But that's just a naming convention thing to help organize stuff. Okay, so now that we've got our data in our shader as a vec2, we can use it. And again, the goal of the vertex shader is to transform our vertex data in some way. In our case, though, there's no transformation that needs to happen. We don't have a camera system yet. We don't need to complicate stuff. We're just going to take in the data and then output that exact data. Exact, not really. Note that this is a vec4. GL position expects a vec4 because, again, OpenGL is set up to do 3D operations, and all of the 3D stuff happen, all the 3D calculations happen in 4 dimensions. So GL position expects a vec4. So we just use this sort of constructor here, which is very nice. It takes in a vec2 as the first argument, so the x and y values of that vec4, and then the Z value is going to be 0, and the W value, which is not used, is going to be 1. Now GL position is I don't know what to call it. It's like a variable that automatically exists in the shaders. And this is what I meant when I said the output of the vertex shader is the location of a vertex. This is the output. GL position is the variable you output to. You don't like return from the function, but essentially that's what this is doing. So we're putting our position value as the output value, and that's what OpenGL will use. And that's what the default shader that's running right now does. If I just run this again real quick, you can see I have this rectangle in the middle of my screen. It's like it's data that makes sense, right? Because I have these coordinates, bottom left, top left, and the output corresponds to that. So whatever default shader OpenGL is using probably has exactly this same code. But I'm just writing this again as a sort of an introduction, and we will be obviously doing a lot more interesting stuff with our shaders. So now we have the part that actually matters in this case, which is the fragment source, the fragment shader. So we're going to have that same version 330 core. Then we're going to have, again, layout location equals 0. This time it's a bit different though. This is an output variable. And similar to how I said GL position is like an existing variable that stores the output of the vertex shader, this is how you output the pixel color. It used to be that there was a very similar variable called like GL frag color or something like that, and you would assign to it in exactly the same way, and that would be the output. I'm not sure why they changed it. Probably they introduced some new stuff into the pipeline and they wanted to make it more consistent. I don't know why. But just know that this line, the location equals 0 here, because it's an output variable, refers to nothing in our data. It has nothing to do with that. This location equals 0 is something that is internal to OpenGL, and it reads from that as the pixel color. So it is an output variable. It is vec4, because remember I said pixels are given RGB and alpha values. So it's vec4 instead of a vec3, and it doesn't matter what you call it. But as I said before, I do my output variables as O underscore, and if they're in a vertex shader, I do V underscore, but we'll see that in a bit. Probably not today, actually, but later on. So we have the same sort of familiar void main syntax, same as the vertex source, same as C, C++, and we're just going to assign to this output variable. Now, it takes a vec4, and we can give it anything we want here. For the sake of example, I'm just going to give it red. So the way you should read this shader is, okay, I can ignore that. That's just telling me what version of OpenGL to use. This says, okay, I have this variable that I'm outputting to at location 0. That's going to be the color of my pixel. I have my main function here, which runs. And then to this output variable, I'm giving for every single pixel 1001. So that is red, 0 green, 0 blue, and 1 alpha. And the alpha does actually matter here, because if you give it something less than 1, it will blend it with your background color, or your clear color, which for us is blue. So I'm just going to give it 1. So essentially, when we finish doing our shaders, instead of a black rectangle, we should have a solid red rectangle. Okay, now that we have our shader source, we have to send that source to the GPU. We have to sort of give it to these shader programs that we've created up here. And we do that with GL shader source. So we give it the GL uint shader, the pointer to our shader, the number of sources, it's going to be 1, a pointer to the string, so and vertex source, and the length. So this length is used if you want to use part of the string, but if you want to use the whole string, you give null pointer. So that's for vertex shader. We'll do the same for our fragment shader, except passing fragment as the pointer and fragment source as the string. Okay, so now that our programs have our source code, they need to compile that source code. So we'll do that with GL compile shader. on Vertex, and on Fragment. So I think I'm going to skip for now in the interest of time, but there is some like error handling code that I'll probably add just on my own for next week for Wednesday when you download from the GitHub repository. It's very boring, it's very self-explanatory, but basically you can just say, okay, did this compilation fail, did this compilation fail, and then print out an appropriate error message. So I'll write that here, error handling. But these shaders are so simple, there's nothing wrong. I hope I'm not speaking too soon on that. So now that we have our shaders, we need to combine them into a program. Now, I think the best way to think about a program is if I open back up this presentation just real quick, and I go to that slide, this one right here. So we have transform vertices in the Vertex Shader, rasterization, and then color the pixels in the Fragment Shader. So the program is essentially this whole box. Except for rasterization, which remember is automatic, you can't change that. A program contains multiple shaders. In our case, just a vertex and fragment. There are other kinds, but we won't be using them. So it's just a way to sort of combine multiple things into one thing. So we do that with GL create program. And then we need to attach our shaders to that program. It takes the program ID, the shader ID, and of course, we're doing this for both our vertex and fragment shaders. Then we need to link this program and then validate the program. So this is sort of, I guess, similar to how like a C++ compiler works, is linking stuff together if you reference different things in multiple files. But I don't think we'll be doing any of that. And then once you've done this, once you've like uploaded your shader to the program, compiled the program and everything, you can delete the shaders themselves, because this essentially just copies all of this into the program. And so the original version you don't need anymore. So we do that with GL delete shader on vertex and on fragment. Okay, and now we should still get black, which is good, because we forgot the most important thing, binding. OpenGL, I've heard it described as a state machine. Whatever is like in a slot that OpenGL uses will stay there. But if you don't put anything in there, there won't be anything in there. So we need to, every frame again, we need to bind our shader. Say, hey, use this shader. Now we should get a solid red rectangle. Beautiful. Not beautiful. Very boring. But everything worked. And you can see I can change the color if I want an extremely ugly magenta rectangle. I can set the blue to 1 as well. And while I'm here, I'll actually just show you what happens if I set the alpha value to 0.5. It'll blend our red with the background blue and give this weird purple. So that's what that fourth value does. But I'll leave that as 1. Okay, so that's all we have time for today. I think I was going too fast. Sorry about that. But this stuff, I really wanted to get through like this basic setup, just because trying to pick this up like in the middle of shader compilation would be a pain next time, and I'd probably have to redo it all anyways. So yeah, you're gonna have to go back and watch the video on this one. But what we've done here, I'll give a quick recap, because we did a lot. Like, this is a lot of progress. And next time we're going to do a bit more, some interesting work with the shaders, and then start wrapping everything, which is the real task, like the actual interesting part of, okay, how do I take all this ugly, line by line, just OpenGL code that sucks and it's really just like there's stuff all over the place. How do I take that? How do I separate it out in an organized way that makes sense, and then use that in my program instead of having to do all of this ugly stuff? So that's what we're going to be doing next time. But what we did today was we created Vertex Data on our GPU. We created a Vertex Array, which stores a Vertex buffer, which actually has that Vertex data, as well as the description of that buffer, which tells OpenGL, hey, here's what my Vertex data is. So we did that, Vertex Array, gen buffers, buffer data, send the data to the GPU, and then we told it, hey, these are 2 floats per vertex, they're not normalized, all that stuff. We created an index buffer into our vertex buffer, so that even though we're drawing a square here, which does require 2 triangles, which theoretically is 6 vertices, we are sharing just 4 vertices, so we don't have to repeat any data by using these indices going in counterclockwise order from the bottom left, binding that to the element array buffer instead of just the array buffer. Then, obviously, we created our shaders. This vertex shader, which runs once for each vertex. I should say each vertex that's being drawn. That's probably a better way to put that. Because if I say each vertex, you might say, oh, okay, so 4 times, because we have 4 vertices. No, it's running once for each vertex that is drawn. And in our case, that is 6, because we have these 6 indices that are being used. So for all 6 of our vertices, we are taking in a vec2 from our vertex data. A vec2 is just 2 floats. And then we are essentially just outputting that, but transformed a little bit into a vec4 that the GL position wants. Then for each pixel within each triangle that is drawn, we are setting the pixel color just to a flat red and outputting that in sort of a weird way to where OpenGL expects it to be. Then we give these source code strings to the shaders, compile the shaders, create a program to store both the shaders, attach both the shaders to that program, finalize the program, and then delete the original shaders because they are now contained within the program. Then each frame, while our game is running, so while we don't hit the X button or like Alt F4 or whatever, at the start of the frame, we clear the color. Because if the camera is moved around or whatever, you don't want sort of remnants from the last frame to be there. You want to clear the screen and start fresh. We say use our program, use these shaders to handle how you draw stuff. Bind our vertex array, so this is the actual vertex data you're going to be using. Here's the index data you're going to be using into that vertex array. Draw using the GL triangles method and draw the index buffer that I've bound. Then, once you've drawn all of that, swap the buffers, so put what you just drew onto the screen, and then handle events, which we aren't going to do. And then once you've closed your program, this loop terminates, and we clean everything up with the GFX end function, just closing down GLFW, destroying our window correctly, all of that stuff. And once again, here's the output. Very boring, but you can see now and hopefully sort of appreciate the complexity of OpenGL. It took, let's see. This is about 80 lines here. This is about another 80 lines, so 160 lines of code to draw a red rectangle on our screen. There are, good reasons for all of this because, once again, it is not a 2D graphics library, it is 3D, and so there's a lot more complicated stuff that it needs to be able to handle. But in our case, we're not using most of that. We just have to put up with all the extra overhead that is required. So yeah, hopefully, even though I was going too fast for you to follow, you learned some stuff. You can go back and watch the video and copy all this down. If you have any questions about this stuff, please ask me, because this is sort of like, again, foundational. Like, we're going to do a bit more with it next time with the shader sources, but that's it. And then we're going to start putting it all into libraries. So, abstracting it all into classes within our library. And once we start doing that, like, I'm basically assuming that you know what all of this stuff is, and so you will be able to understand why I make the decisions I make about how to organize it all. So yeah, sorry for going so fast, but I'm glad we got through this. I think it's very interesting. Hopefully you do too. But I'm excited to pick up on Wednesday with some more shader stuff, and then cleaning all this up so it's not 160 lines of ugly code.